Okay, it looks like we have close to 80 people in here. We're streaming live on YouTube, so I'm going to get started in just a moment. Hello, everyone. My name is Rick Feinberg. I'm the press officer of the American Astronomical Society, and I'm very happy to welcome you this afternoon, or at least here on the East Coast of the US, to a press conference on conclusions from the Satellite Constellations 1 workshop, or SATCON1. The workshop was held in late June and early July, and it brought together more than 250 scientists, engineers, satellite operators, and other stakeholders to discuss the impact of satellite constellations on optical astronomy and recommendations toward mitigating those impacts. This is a joint briefing. It's being hosted by the American Astronomical Society, or AAS, and NSF's NOIRLab, which is operated for the National Science Foundation by the Association of Universities for Research in Astronomy, or AURA. We can have the next slide. This just identifies who I am, or at least my affiliation. Move on to the next slide. I want to mention that the report about which this briefing is being held for is available now. We just published it live on both the AAS and the NOIRLab websites, along with the press release that's now winging its way to people on the AAS press list and via other distribution channels. So before we actually get into the presentations about the report, I want to introduce a couple of VIPs to offer some words of welcome. The first, if we go on to the next slide, is Ralph Gom. He's the director of the Division of Astronomical Sciences at the National Science Foundation, or NSF, which funded the SATCON1 workshop, and for that we're quite grateful. So Ralph, if you'd like to say a few words.
Thank you, Rick. So, as Rick mentioned, I'm the director of the Division of the Astronomical Sciences at the National Science Foundation. Our role is to support fundamental research in ground-based astronomy and to help ensure the excellence of the US astronomical community. You know, satellites have been visible since the dawn of the space age, but something has changed recently and was recognized about a year ago when large numbers of satellites began launching and began being visible in our nighttime sky. So in order to ensure the excellence of the scientific excellence of the community, NSF's role is to fund research. And so we funded research, as Rick mentioned, into this issue and provided the funding to NSF's National Optical Infrared Astronomy Research Lab, which we call NOIRLab, to conduct a community workshop to look into and to research this problem. So that's where we are today. I'm very pleased to see and to learn the results of this workshop. Rick, back to you.
Thanks very much, Ralph. I'd next like to introduce Phil Puxley. He's the Vice President for Special Projects at AURA, the Association of Universities for Research in Astronomy, which manages the NOIRLab under a cooperative agreement with NSF. Phil?
Thanks, Rick. So astronomers have been concerned for many decades about light pollution, in which the lights from towns and cities reflect off the atmosphere and into the telescope's sensitive instruments. And that has pushed observatories to find increasingly remote, sparsely populated locations to be sighted. The reality of this newly emerging challenge of sunlight reflecting off constellations of satellites down to Earth is that there are no remote locations that are immune. There is no place to hide. And so this workshop was both timely and important to understand the technical impact and the technical mitigations that might be possible. So on behalf of AURA, I'd like to thank Ralph and his team at NSF for its support of this workshop, held in partnership, as you've heard, between NSF's NOIRLab, one of AURA's research centers, and the American Astronomical Society. And I'd like to express my appreciation to the hundreds of people who participated from the US and the international astronomy communities, satellite operators, and other stakeholders interested in the night sky. And importantly, I'd also like to express my appreciation for the very collaborative spirit in which the workshop discussions took place between all those groups. Back to you, Rick.
Thanks very much, Phil. Okay, if we could have the next slide. I'm about to introduce the co-chairs of the Scientific Organizing Committee for the workshop, but before I do, I want to make a few housekeeping announcements. This is primarily for the journalists and scientists and others who are attending. You should see in your Zoom window a Q&A button or icon. If you click that, it should open a Q&A box. This is how you can ask us questions. You can type questions into that Q&A box. When you do so, your name will automatically appear, but we won't remember your affiliation because we had well over 100 people who signed up for this. So if you could please indicate your affiliation. Also indicate who your question is for if it's being directed at a particular panelist, and then ask your question. And we're going to save all the questions till after all the presentations are finished. So we'll have about a half hour of uninterrupted Q&A time at the end. If you see a question that you particularly want to see answered, either you were going to ask it yourself and somebody already did, or you just like the question, you should be able to upvote it. I don't remember exactly what the icon is. I think it might just be a thumbs up, like type of button, but there's something that will let you upvote, and then that'll reorder the priorities of the questions. So the ones that people are most interested in seeing asked will rise to the top. Now, the SATCON1 conference or workshop focused on scientific and technical issues. We know that everybody's interested in contentious issues of policy, regulation, the merits of launching tens of thousands of satellites in order to provide internet service worldwide. All of these issues are going to be addressed in SATCON2, a conference or workshop, sorry, that we're planning to hold in the first half of 2021. Date's not set yet. So please, if you have questions of that nature, best just to hold them till we have a panel assembled who's truly prepared to answer those kind of questions. I also want to say that if we have way more questions than we have time for, we're going to do our best to pick questions that journalists have asked. This is a press conference after all. Everybody's welcome to ask questions. That includes scientists and engineers who are tuned in. But if we can identify the journalists and their questions haven't been answered yet, we're going to try to get to those. All right, so now let me introduce the co-chairs of the workshop, or specifically of the Scientific Organizing Committee. Connie Walker is a scientist at NOIRLab in Tucson, Arizona. That's where the headquarters is. She's a member of the AAS Committee on Light Pollution, Space Debris, and Radio Interference. She runs the Globe at Night Citizen Science Project to measure dark skies around the world. And she's president of the International Astronomical Union's Commission B7, Protection of Existing and Potential Observatory Sites. Jeff Hall is the director of Lowell Observatory in Flagstaff, Arizona. He's the chair of our AAS Committee on Light Pollution, Space Debris, and Radio Interference. In addition to his research on solar and stellar astrophysics, he plays a very active role in dark sky preservation efforts throughout Arizona. So now I will turn it over to Connie and Jeff and mute my own audio and video. And we can advance to the next slide, I guess.
Yes, please. Thank you, Rick. Hello, everyone. Right now, we are experiencing a major intersection of technologies between deep, wide-field sky surveys and potentially large numbers of Earth-orbiting satellite constellations. For instance, with the tens of thousands of possible Starlink satellites, SpaceX's capability to provide internet service to billions of people worldwide has definite merits. At the same time, there is a tremendous amount of new technology coming online within the field of astronomy in the next decade that will substantially increase humanity's understanding of the universe. However, observatories require a dark night sky to uncover the secrets of some of those fundamental questions about the universe. Prime examples of these new technologies are the Vera Rubin Observatory and the 30-meter telescopes coming online in the next decade. For reasons of expense, maintenance, and instrumentation, such facilities cannot be launched into space or operated from it. Ground-based astronomy is and will remain vital and relevant. Jeff?
Could we have the next slide? So we were very pleased to have quite a large attendance at the SATCON1 workshop from around the world. There were 53 individuals who comprised the scientific organizing committee and the 4 working groups that we charged in advance of the workshop to look at 4 critical aspects of the problem and generate reports that would be would set the stage for the discussions during the 4 days of the workshop. Of our 250 attendees, it was mostly from astronomy, but we had active participation by SpaceX engineers, staff from Amazon Kuiper, as well as a former employee of OneWeb prior to their bankruptcy, also attended the workshop. So there was active interest and participation from the operators, as well as diverse stakeholders such as dark sky advocates, amateur astronomical societies, astrophotographers, national and state parks. So it was a very broad engagement that we had from the community. As Rick noted, we focused very specifically on the current observations and assessing the impacts of the satellite constellations and coming to some initial conclusions about what we can do to mitigate the impact of the constellations on ground-based astronomy. So being released today is our summary report that we have been writing, the scientific organizing committee wrote over the 2 months following the workshop. And the 4 reports from the working groups provide the foundation for that. And as noted by Rick, these are now all available online, available for your perusal. And we will be reviewing the basic conclusions from the summary report for you today. Connie?
Thank you. Next slide. For instance, the main takeaway from our findings is that no combination of mitigations will eliminate the impact of satellite constellations on optical astronomy. Next slide, please. Okay. That said, I will summarize the options to reduce impact here. Not launching satellite constellations. While this may be an option, it's not viable for industry. Keeping them low, for instance, less than 600 kilometers in altitude. Darkening satellites in all phases of the orbit, including launch, parking orbit, final orbit, and decay. Darkening satellites on station or final orbit to a fainter than 7th magnitude. Orienting satellites with the edge of the satellite toward the Earth so you have less surface, so you would reflect less sunlight. Removing or masking trails in images using software techniques. That said, this may not be feasible for many science programs. Avoiding satellite constellations using advanced pointing algorithms for avoidance of bright satellites. That said, again, this may not be feasible for many science programs. These and other findings will be further explained in our working group by our working group chairs. Next slide, please. Jeff?
Right, and so I will very briefly summarize the recommendations that we came up with. There are 10 of them. A little later in the conference, our metrics working group chair, Richard Green, will discuss these in a bit more detail. But at a broad brush level, we identified several things that observatories can do and can be supported to do. And this principally includes developing and improving the suite of software tools we have available, both to mask and mitigate satellite trails that are going to be inevitable in the images, as well as improved tools to predict the locations of the satellites, and just so we can know where the ground tracks are with greater precision. So that's something observatories can do. Next slide. We identified a number of things that we would recommend that operators do, and these chiefly involve both the design as well as the deployment of the satellites. So satellites can be designed to be darker, less reflective, and that can be done ground up from the very earliest stages of design, both to darken their overall brightness as well as to minimize the appearance of flares as the phase angle to the satellite changes as it goes by. There are also things that can be done in terms of the orbit raise phase for adjusting the satellite attitude so that a smaller reflective surface is facing the ground. And they can be configured in ways that minimize their impact. Next slide. Finally, we will later in the conference review some things that we feel observatories and satellite operators can do collaboratively, which includes a much more comprehensive network to observe and assess the brightnesses of these constellations or in orbit rays on station. And we also really identify we need to greatly increase the precision of publicly available positions. They're not accurate enough for observatories to work around some of the issues that we're facing. I would like to conclude this part by noting that we really did identify things where we feel observatories and satellite operators can work collaboratively. And I'd just like to reiterate Phil Puxley's comment that this has been a very constructive and collaborative process throughout. It's been a real pleasure getting to know Patricia Cooper and Jared Green from SpaceX. They have put in an immense amount of time and effort to work with us to minimize the impacts of the Starlink constellation on ground-based astronomy. We have also, I'm actually answering one of the questions that's already in the Q&A. We have had a number of messages back and forth with Amazon Kuiper, and as I noted before, they also attended the workshop, and we're definitely looking forward to collaboration with them going forward. Prior to OneWeb's bankruptcy, Connie and I and a number of our committee had an initial very constructive telecon with them as well. So we really see that in this whole process, SpaceX has set an excellent example of a collaborative effort between astronomy and industry to manage this problem, and we certainly hope to see other operators following suit as we go forward. Really appreciate that and look forward to all the work going forward as we head towards SATCON2 and start moving into the policy arena. So with that, I'll turn it back to Connie to introduce our working group chairs.
Okay, next slide, please. So I'm going to introduce all of them here before we get on to the first presentation by Lori. So it is my pleasure to introduce you to Lori Allen, who is the director of the Mid-Scale Observatories, or MSO, at NOIRLab, and is the chair of the SATCON1 Observations Working Group. Pat Zeitzer is a research fellow emeritus of astronomy at the University of Michigan and is an expert in space situational awareness and optical studies of orbital debris, as well as the chair of the SATCON1 Simulations Working Group. Tony Tyson is a distinguished professor of physics at the University of University of California, sorry, Tony, Davis, as well as the project scientist for the Rubin Observatory. He is also the chair of the SATCON1 Mitigations Working Group. Richard Green is the assistant director for government relations at Stewart Observatory, which is part of the University of Arizona, and he is also the chair of the SATCON1 Metrics Working Group. And all of us are proud members of the AAS Light Pollution, Radio Interference, and Space Debris Committee, which Jeff Hall chairs. So with that, I'd like to turn it over to Lori to do her presentation from the Observations Working Group.
My first slide, please, Kelsey. Thank you, Connie. It's a pleasure to be with you today. As Connie said, I'm an astronomer at NSF's NOIRLab. Next slide, Kelsey. So you may be wondering if we're worried about satellite trails showing up in our data, why are we intentionally observing them? Well, there are a few reasons. We know that there will be more in the future, and even with mitigations that we employ over time, we know that some of them will continue to land in our data. So we'd like to understand their impacts on the science of astronomy now by making measurements of their brightnesses and other characteristics and quantifying those impacts, as well as ways to mitigate those impacts. And as we develop and employ various mitigation solutions, we want to have the ability to make observations of the modified satellites to test whether or not those mitigations are effective. So pictured here is an image of an unintentional observation of low Earth orbit satellites. This is a Starlink launch group imaged by the Blanco 4-meter telescope on Cerro Tololo in the fall. And while this was serendipitous, the observer was not expecting satellites to pass through the field of view. It is an illustration that we can actually observe these. And so what I'm going to talk about today are intentional observations. Next slide, please. So what we have found by studying the observations to date of LEOsats is that these observations do have their challenges. They are a little bit different from standard deep sky observations of celestial objects in that they're moving much faster than typical celestial objects on the sky. That means we need accurate information about their position and the timing of their launch and deployment so that we can locate them precisely enough to get a measurement. Nevertheless, we find that mitigation attempts on satellites are in fact measurable. Here is a plot of measurement of DarkSat, AKA Starlink 1130. And it was measured with 4 of its cohorts from the same launch group. DarkSat had been modified to darken some of its surfaces, make them less reflective. And as you can see from this plot, it's about a magnitude fainter than its cohorts, which is a factor of about 2.5 in brightness. And finally, we find that a major finding is that we don't need large telescopes like the Blanco 4-meter to do this. Smaller telescopes can be employed as long as we employ them with a set of uniform standards. And that means many more people can participate. Next slide, please. So our recommendations are that we need a coordinated effort to observe LEOsats now for the characterization of these satellites and for the understanding of their impacts. This requires multiple measurements of the satellite brightnesses at a wide range of deployment stages and illumination angles. And so we need multiple observatory sites and multiple telescopes engaged in this process. We need to make measurements of their flare and glint behaviors where they suddenly will brighten by several magnitudes for a brief period of time. And we need to make these measurements over satellite lifetime cycles because their brightnesses do evolve depending on their altitude and their orientation in the sky. So here are a couple of images obtained by the Pomenas Observatory. On the left are 2 Starlink satellites launched together, but with very different brightnesses, presumably because of their, they are showing different orientations with respect to the sun and the earth. And on the right is a Starlink satellite in flare mode. Next slide, please. And our second recommendation is to form a comprehensive satellite constellation observing network. We need to be able to connect the interested observers with telescopes, provide very good, precise observing protocols and data analysis standards so that all of the data can be compared on the same basis. We need to coordinate these observations together, and we need to prepare for future generations of objects in the sky. So here is a contribution from, again, the Pomenas Observatory, and I'm pointing it out because it's a small telescope pictured here, put together by a graduate student at the University of Arizona, Harry Krantz, who works in the Space Situational Awareness Department. And he has accumulated hundreds of observations of Starlink brightnesses using this telescope. And so this is accessible to smaller apertures. And I will stop there. Turn it over to Pat.
Okay, thank you very much. So I was the chair of the simulations working group, and which did simulations of what constellations will look like to astronomers. If I could have the next slide, please. So there's an estimated 107,000 LEOsats planned to be launched in the next decade. That's from a study from AGI. And we modeled the visibility, that is, how many of these satellites will be visible, when will they be visible, and where will they be visible in the night sky for the three largest of these constellations that we know of. And these three constellations, Amazon, Kuiper, OneWeb, and SpaceX, represent more than 70% of that estimated 107,000 LEOsats that are planned. So one of the things we wanted to address was, are some constellation architectures more challenging for astronomy? And that's where that 600 kilometer limit comes from. So if I can have the next slide, please. So it was great to work with a group. There were 6 groups and individuals doing simulations, 4 in Europe, 2 in the United States, plus 1 group in the United States doing brightness simulations. All of us worked completely independently. We did not share software or algorithms. We had a test constellation of 10,000 satellites, and we worked through, and our results agreed very, very well. If I can have the next slide, please. So this shows you our standard test constellation, which had 10,000 satellites, 100 planes with 100 satellites per plane at an inclination of 53 degrees. And it shows you running from sunset on the left to sunrise on the right, how many satellites are above 30 degrees elevation at any one time. And so one of the key findings of all of the simulations was that the higher altitude constellations are more challenging for astronomy, because during the summer, they are visible all night long. Remember, they're out of Earth's shadow. We see them by reflected sunlight. The Earth's shadow is a cone, not a cylinder. And so lower altitude satellites go into Earth's shadow sooner than the higher altitude ones. And so the takeaway for the 600 kilometer limit is that the higher altitude ones are much more dangerous. So I would encourage you to go to the working group, to the summary report and to the working group report, because you'll see extensive simulations of real constellations in those reports as a function of time of year, as a function of where the observatory is located. And I encourage you to follow those up. So next slide, please. So the simulation summary was that there's a fraction of the satellites of each constellation that'll be visible at any observatory at any one time. And you can read what the limits are here. Most of the satellites appear at a low elevation over the horizon, typically 50% below 10 degrees. But 50% above 10 degrees is still a very significant challenge for astronomers. The number of satellites visible is a function of their orbital inclination, peaking at a latitude close to the inclination, orbital inclination. And the constellation with the greatest impact for any observatory in terms of the number of satellites visible, the number of satellites that will be in sunlight, will be the one at a higher altitude and with an orbital inclination close to the latitude of the observatory. So if I can go to the next slide, please. One of the real striking findings here was just the impact it will have on observations of the Large Magellanic Cloud. This is the largest satellite galaxy of our own Milky Way. It's best observed, that is, it's highest in the sky in the summer in the southern hemisphere. If a large constellation like OneWeb, 47,000 satellites at 1,200 kilometers is launched, every 30-second exposure will have at least one satellite trail. Every 30-second exposure of this, no matter the time of night, during the summer in the southern hemisphere, will have at least one satellite trail. And that is a great challenge for astronomers. So if I can have the final slide, please. So our recommendations going forward for future work are to simulate the impact on science of these constellations. How often will a specific observation of an astronomical object be lost to a satellite trail? What's also very important is to simulate the other 2 phases of a constellation lifetime. An initial mission phase, parking orbit and orbit raise, and the deorbit phase. If we have 100,000 satellites in a steady state configuration with a lifetime of 10 years, that means you are launching 10,000 satellites every year to replenish. 10,000 satellites are deorbiting at the end of lifetime. And so every year you have 20,000 satellites whose orbits are changing. And we need to simulate just what the effects of those are. Finally, we'd like to do high fidelity simulations of the observed brightness, which is a function of many, many things, including the defocus expected for satellites at small ranges. So with that, I'll turn it over to the next. Thank you.
Hello, everybody. Glad you're with us. We had a working group called Mitigations Working Group to look into all possible mitigations, not only from the point of view of observing, but also from the operator's point of view. Next slide, please. So as a result of this extensive study, we found that all optical astronomy observatories will be affected to some degree by the light pollution caused by low Earth orbiting satellites. The issue really is the frequency, the rate at which these trails appear in the data, and also their brightness. Both of those have an effect on the science itself. The Rubin Observatory itself would be particularly impacted because of its unprecedented product of light collection and the wide field of view per exposure. It's making a digital color motion picture of the universe, so it's a perfect machine, unfortunately, to run into these things. Next slide, please. One of the issues that we discovered early on last year, we simulated a Starlink satellite trail on one of the CCDs that we use in our camera in the lab, and we discovered that when it's illuminated with a trail that was equal to what we saw in the original version 0.9 satellites, we had these electronic echoes that were caused within the CCD itself. And we can get rid of them in software if and only if we can, somebody can darken the satellites to fainter than apparent magnitude 7. We have found that that's a possibility only in that case. Next slide, please. So that set a goal. SpaceX has been working with us on this to address mitigation. As you heard earlier, they've been attempting to darken their satellites. We found that making the Starlinks about 10 times darker than the original satellites can remove some of these electronic echoes, satellite trail artifacts. But even if we are successful, completely successful in doing that, the satellite trail itself is still left. The artifacts are gone, but the trail is still there. And the existence of these trails in the data vastly complicates data analysis and limits the discoveries. That also coincidentally led to a 7th magnitude limit. Next slide, please. With tens of thousands of LEOsats as planned, we found that generally no combination of mitigations, of all the mitigations we studied, can completely avoid the impacts of LEO satellites on the science programs of the coming generation of optical astronomy facilities. These facilities are actually designed to probe the dark sky to unprecedented faintness. For dynamic events, they will require fewer and fainter LEOsats to realize their full potential. Rubin Observatory's LSST opens the prospect of discovering the unexpected, especially in the time domain. And this is precisely the discovery space that is most at risk from artifacts arising from tens of thousands of LEOsats. Next slide, please. So we came up with some recommendations. This is a few of them. First of all, as you've heard before, darkening the satellites in all phases of the orbit: launch, parking, final orbit, and decay. Darkening them specifically to 7th magnitude in the visual band. And that translates to something that operators can actually address, mainly luminance, irradiance rather, of 44 watts per steradian. And that's something that a satellite operator can introduce in the design process. Fewer satellites would work, and there are probably ways of doing that. No satellites above 600 kilometers. You heard about this before from Pat. This is for a few reasons. And the important effect here is that the satellites that have been proposed, for example, at 1,200 kilometers, can be seen all night long. They're illuminated all night long. So there's no place to hide in the middle of the night from such a satellite constellation. But there are other effects, mainly that there are more in focus for our big telescopes and therefore appear brighter in surface brightness. So that's really a dangerous place to be in terms of impact on science. We need high accuracy orbit time information, an app, for example, for all of us to use, whether amateur or professional, for LEOSat position time prediction. Advanced pointing algorithms, we're working on them for trying to avoid the brightest of the bright satellites. And a predictive model for satellite brightness versus orbit relative to the observatory. In principle, this is possible if for a well-studied, well-designed satellite surface. And finally, the biggie, support for full end-to-end simulations of the science impact by the research community. Next slide, please. So this is Richard Green. He's going to tell you about these metrics working group.
Thanks, Tony. And next slide, please, Kelsey. So our group really ended up having the responsibility for taking all this excellent input and distilling it into some coherent recommendations and findings. And so you will now hear a summary of what you've just heard. The context of all of this is that there's a rapid phase change where nighttime images without the passage of a sun-illuminated satellite will no longer be the norm for a ground-based observation. So as Jeff told you, there are three general categories of recommendations: what astronomers will need in the very short term for mitigations, what we encourage operators to do to help us out, and how we need to collaborate with operators on certain aspects of this so that the two communities together can end up in a better situation. So next slide. So here are the formal recommendations in the report. Astronomers are just starting to get their arms around the challenges of having satellite trails in most images. And so it would be extraordinarily helpful to have a general user algorithm that can find and mask out these trails. Secondly, observatories need to have a readily available tool so that you say, I want to point at this place on the sky at this time of the night, you can then predict which satellites will possibly go through that field and avoid it if you can. And third, as Tony just said, there's a whole world of analysis that needs a lot deeper simulation. What happens when you have a large linear masked area on an image for your analysis of linear features in an image? How do we keep systematics at very low level from rippling through? Next slide, please. For the operators, if they can design their unit satellites from the beginning to have the lowest possible reflectivity, it would really help. If they could both measure and model to give some hope that they will meet those goals, that will be excellent. Tony just explained to you that to keep the Rubin Observatory detector in calibratable range, that has a specific correspondence, and it turns out that the brightness depends roughly linearly with orbital height, so that the reflectivity, so that it needs to be, the objects need to be fainter when you're going up. Operators have to make we hope they will make best efforts not to have shiny mirrors on some surface that faces the ground so that it can avoid the flares that pop the apparent brightness well over that average limit that we just talked about. Next slide. And finally, just a technical point, those stunning families of streaks actually help, because if post-launch the constellation stays tightly clumped within safety limits, the whole thing passes through your field very quickly and you can actually avoid them because those satellites will be very bright. Also, managing the spacecraft attitude during those phases would be very helpful to minimize reflections. Next slide. So what do we need to do together? You heard Laurie Allen's discussion of a network of ground-based observing so that you get the variation with solar phase angle, that you monitor the satellites as they go through phases of change like orbital boost or deorbit. And so, and even on station, it will, the reflectivity will change with time. So this needs to become a whole enterprise, also to validate the operator's attempts to keep the reflectivity low. Next slide. It's easy for astronomers to specify how accurately we would like to know the position of a satellite as it goes through its orbit. It turns out we're at least an order of magnitude off, according to our interaction with the SpaceX orbital mechanics engineers and scientists in the current protocols. And so we need to work together to get much closer to the accuracy that's needed. And that includes propagating information in a way that has a new format compared to the 60s level version that's now shared. Next slide. So as Pat told you, the high orbits are the ones that are the most impactful on astronomical observations. And so we present that as a finding, but it is a true statement. And it's going to, if there really are tens of thousands of LEOsats, no combination of mitigations can avoid the impact. We just want to try to work to make it as low as possible. And we do point out that for now, the working together between astronomers and the satellite operators is a very positive way forward for finding technical mitigations to these issues. And we hope to continue in that way and broaden our interaction with the satellite operator community. So that's it.
Okay, thank you very much to all our panelists for those great presentations. We're going to be heading into the Q&A in a moment. I want to remind everybody that there will be another workshop, SATCON2, planned for first half of next year, and that you should watch both the American Astronomical Society and NOIRLab websites and press release feeds for news about that. We're going to now go into the Q&A, and I want to mention that my colleague, Lars Lindberg Christensen, who's head of communications, education, and engagement at NSF's NOIRLab. He'll be sorting and reading the questions with some backup from his colleague Amanda Koch, the press and internal communications officer at NOIRLab. And they're going to read some questions out loud, and we'll take as many as we can. Again, the reason we're doing this aloud is so people who are following along on YouTube and can't see this Q&A box are able to hear the questions and the answers. So with that, I'll turn it over to Lars.
Thanks, Rick. Yeah, so we have quite a lot of questions here coming. The top ranked one is from Alex Witzke from Nature. She asks, SpaceX was very involved in the SATCON1 workshop. What conversations have you had with representatives from OneWeb, Amazon, and other operators? And Tony Tyson would like to take this one.
Yeah, so clearly SpaceX is leading the charge in terms of trying to understand these issues and designing mitigations on their satellites. Others are getting interested, and in particular, as you mentioned, Amazon and OneWeb. I've been contacted by both of them, but we're nowhere near any kind of down-to-earth engineering discussions on how to do this. We've just been contacted, and they did attend the workshop, by the way, so that's a good sign.
All right, and then we have a question for Laurie Allen from Monica Young at Sky and Telescope magazine. Thank you for going over the dark-sat observations. SpaceX recently instituted several mitigations, including changes to orientation. Do we have observations that show the effect of these mitigations?
So we don't have a complete set of observations yet of the visored satellites. We do have some initial observations, but those are still under analysis. And it's just one, it's a limited sample. And we really, we'll need more data before we can say anything. So that is just starting. We're a little bit hampered by the fact that many telescopes are still shut down due to the pandemic. And so not as many apertures are available on the sky as we normally have, but we are working on that.
Thanks, Laurie. So I guess that also answers Jeff Faust's question. He's from Space News. Do we have any good measurements? Amateurs estimate magnitude 7, but little else is reported. So I guess the answer is we just don't have the data yet. Is that correct?
That's right.
All right. Then we have a question about one more about VisoSat. Are any of the mitigations more important than others? Is it more crucial to have visors, or is the orbital altitude more important? Does anyone want to talk to that one?
I can attempt to talk to that. There are various effects, as you heard. There's the apparent continuous kind of brightness that a satellite has as it passes through the field of view of the telescope. And then there is occasional flares or glints off of sort of mirror-like surfaces on the satellite. These cause two different issues. And so both of those have to be addressed in the design of the satellite. I think that answers the question.
Thank you very much. Then there is a tricky question about the Kessler syndrome. So it's a bit in the periphery of what was dealt with in this workshop. But nonetheless, it's an interesting question. So even if we can't answer it, I'd like to read it out. So Ethan Siegel, freelance, is writing the ultimate nightmare scenario that some have envisioned would be the Kessler syndrome. So a collision of two LEO sats that would set off a chain reaction of collisions. There are AI-controlled collision avoidance systems, but they could potentially be knocked out by a solar flare. Has any science been done to look into this and quantify the risk, considering the number of LEO sats, and is this a likely event? Does anyone want to answer this? And if not, that's also perfectly okay.
All right, this is Pat Seitzer. I'll take a stab at that. There have been very large studies done on the orbital debris implications of very large constellations of satellites. We will make a list of them and put them on the website, basically by the NASA Orbital Debris Program Office, by the European Space Agency's Space Debris Office, and by various other groups that have published them in the IAC, International Astronomical Community, and elsewhere. Active debris or active control is certainly very vital in this event, and also how long the satellites remain after end of mission. But we'll put a list of those together on the website and you can pursue them. I'm sorry, I don't have a direct answer right now.
It's a very interesting question nonetheless. Then Jim Schweitzer, SCC, is asking about amateurs or people with smaller telescopes like citizen science telescopes or EV telescopes. There are programs managed by the SETI Institute. Hundreds of such telescopes could be deployed around the world. Can they make any contribution to this field? Well, I guess especially right now during COVID-19, where many of the big professional observatories are out of commission.
Yeah, sure. I'll take that one, Lars. Yeah, absolutely. There's a lot of room here for amateur astronomers and night sky enthusiasts to contribute to the database. We would like to do it in a way that is coordinated and with certain standards and controls in place so that the results that are gleaned from those observations will be accurate and scientifically meaningful. That sort of coordination, I think, will require more effort than we've put into this to date, but that is in fact something that could be done as part of a coordinated observatory network in the future to work on this.
Thanks, Lori. Stephen Clark from Spaceflight Now, he's asking, so we heard about these mitigations, darker coding, orientation changes, and sunshades, but has any other mitigation steps been discussed by the operators if those known mitigations are not good enough for ground-based astronomy? Do we have a volunteer for that one? Tony, are you up for answering this?
Sorry, could you repeat the question?
Yeah, of the known mitigations, if those are not good enough for ground-based astronomy, has anything beyond codings, orientation, sunshades been discussed by the operators themselves?
Well, as I mentioned, we've been working closely with engineers at SpaceX. I think we've explored all of the parameter space allowed by physics. No, I think other than being clever and launching fewer satellites and doing something else, no. The techniques that are being used to darken the satellites are many, not just one, not just a visor. And those are being introduced one after the other to try to find out what is most appropriate.
Great, thanks, Tony. So Mabel Angelo from Canal Sur TV asks, what about conversations with operators about software? So this was mentioned in the report. So have those conversations already started, or are they in their infancy now? Do we have anyone experts in that particular area?
I can try to attack that question a bit. The SpaceX folks have expressed a great deal of interest in this, in trying to work with us to improve the artificial intelligent neural net algorithms that we use for pointing. And so that's one area that we're working together on. There are other software issues having to do with, I think there's a question that appeared here in the Q&A. There's other software issues having to do with is there a standard? How do you get rid of these trails, which will be in the data? And it's a real challenge. And we really looked into this in great detail recently. And for a number of technical reasons, it's a very big challenge. These trails are bright. They're actually out of focus slightly. And so they're actually wide, and they wipe out a fair fraction of the pixels on the CCDs that they cross. And the algorithms are still in the experimental phase and not fully successful. So the jury's out on that. That's a serious issue.
Oliver Morton is asking, if there are no satellites above 600 kilometers, are there hours every night that are unaffected by LEOsats? At least that's what the simulations seem to say. And Pat Seitzer would like to try and give that a go.
Okay, it depends very much on how high the satellites get above the horizon. So the model that I showed you was for satellites getting above 30 degrees elevation. And that's a typical limit for astronomers to observe because below that, atmospheric effects start to deteriorate your images. But some astronomers, particularly the large surveys for transient objects and the surveys for killer asteroids, go to 20 degrees elevation. And so even though there may be no satellites visible above 30 degrees, there may be some visible between the 20 and 30 degree elevation limit, and there will certainly be some visible below 20 degrees. So those summer plots that I showed you, which are for 30 degrees elevation, there could be hundreds of satellites still visible below 20 degrees elevation. And I refer you to the detailed simulations that have been done in the summary and in the working group report.
Thanks, Pat. We have one question, which is possibly more for SATCON2, but it could be interesting just to know. This is from Dan Cleary from Science Magazine. Has anyone talked to the UK government? Because the UK is looking into buying into OneWeb. And the question to be asked is, could we ask them to change the constellation orbit of these 1,200 kilometers that are so difficult to deal with?
We'll note that in the discussion in the Q&A, Andrew Williams from European Southern Observatory points out that the Royal Astronomical Society in the UK is now working with the UK Space Agency on that issue. So our astronomer colleagues over there are engaging.
Thanks, Richard. There's something we haven't talked about as radio astronomy. Piero Benvenuti is asking, has anybody analyzed the impact on radio astronomy? And I think we have some experts in the room here with us. Would that be you, Pat, or Connie?
Yeah, I can try if you'd like. Yeah, there's been a lot of work, especially between SpaceX and radio astronomers as a community. In the last 3 to 4 years, they've been talking to each other and regulating, trying to come to agreement on what they can and cannot do with the different bands in radio astronomy. But there has, and I don't really know specifically about the studies, but I'm sure there has been, but it was outside the purview of this particular study that we did for SATCON1. But if anyone else from the group can chime in, I'm all ears.
Yeah, the radio spectrum is a mess, has been for decades. It's oversubscribed, and radio astronomy, a lot of it works by having access to a very broad spectrum. And so you just can't do that kind of work anymore. And so its impact is fairly great on radio astronomy. But as Connie said, it was outside of our purview. But the NSF is actually working with the operators and with the Federal Communications Commission on this. But bear in mind, the FCC oversees only satellites that broadcast to the United States on whatever gigahertz frequencies, not other governments and other operators that don't. So it's a mixed bag. But again, it's outside of the purview of this workshop.
Lars, we can take one more question if you can find one that hasn't been addressed yet.
There is a lot. So Danny Lentz from NASASpaceflight.com is wondering how standardized is the software for creating these mitigations and applying them across a large number of observatories worldwide? I think that's a particularly good one.
Yeah, I tried to answer that earlier. There are various different software challenges and, of course, different software solutions. One area is, for example, avoidance. So software for active avoidance, and that's being worked on. It's not standardized, but again, in the era of tens of thousands of these things, honestly, we have found you can't do that. It just chokes. The system gets jammed. There are just too many of them. You can't avoid them. Mostly because your exposures are too long and there's just too many satellites. There's software for trying to mitigate the effects on the images or the spectroscopy. And again, it depends very much on the application. And there are many applications, and the software is specific to each one. And that's actively being pursued. And as I mentioned before, the jury's out on that. It's quite challenging. These satellite trails are actually quite broad. So a fair fraction of the pixels are impacted.
So I think this answers the question very well, how it will be done. But the issue is more, I think, meant as how can we all benefit? How can different observatories be interoperable and use the same code in different sites? Is that, that sounds very tricky to me.
Well, so there was this idea, actually it came from SpaceX, of having an app that we could all use, amateurs and professionals alike, to tell us precisely when something is going to come across your field of view. And that's quite achievable. So I think I can see the light at the end of that tunnel. The app, the data, the software that we develop at Ribbon Observatory is all public and open. And so any solutions that we come up with can be adopted by anybody.
Thanks, Tony.
Right, I think we'll have to wrap it up there because our hour is up. We did display, or still are displaying, I think, the email addresses for the 6 main panelists. So if you didn't get your question answered and you want to follow up with an email to somebody, please do so. Just a reminder for all attendees to look for the press release and the report documents on the AAS and NOIRLab websites. So I would like to thank our sponsors, the National Science Foundation and AURA and NSF's NOIRLab, and all of my colleagues on our team at the AAS. I'd like to thank all our panelists. You did a great job. Really appreciate it. And all of your colleagues who organized and participated with you in organizing and carrying out the SATCON workshop. I want to thank my trusty assistants today. We have Lars Lindberg Christensen and Amanda Koch helping out with the Q&A, and also they collaborated with me very closely on organizing this briefing and writing our press release. Kelsey Crafton's been hiding in the background, but managing the presentation slides. She's our AAS John Bacall Public Policy Fellow. And I want to thank all of you who tuned in today for your interest, your questions, and for sharing these important results with your colleagues and the public. And with that, I'll turn it off and thank you and look forward to SATCON 2 next year, and we'll do this again. Take care, everybody. Bye-bye.
Thank you.